Hello everyone. Can you hear me? Hello. Check 1 2 3. Hello. So if you can hear me, can you please, if you're looking at this video and if you can hear me, can you please drop a yes on this, yes on the live chat? Good morning, Rahul. How's your breakfast? B. Rajagopal. So, is it necessary to code in C++? It is not necessary, but if you haven't started with a language, it's preferred to start with C++ for competitive programming at least. So, yeah, that's your answer. Hi, Vamshi. How are you all doing? You're doing great. Awesome. So, good morning, everyone. Good morning. I'm Sai Avinash. Sorry for the delay. I'm Sai Avinash. My nickname is Sinus_070. I'm currently working as an SRE at Google Dublin. In this video, I'll be talking about two concepts in modular arithmetic via problems. I'll teach them via problems and the Chinese remainder theorem. But I'm only going to take 2 primes over that instead of many primes. And baby step, giant step. It's used in cryptography as well, and that's a really fun concept. So a little about me. My All India rank in CodeChef is 3, and I'm a 7-star coder. My maximum rating in CodeChef is International Master, and I'm a Master right now. I previously interned at Uber. I'm a snack down finalist. The subjects that I take are discrete maths, dynamic programming, graphs, and a lot of other competitive programming topics that are like appear in contests and so on. Use the code SciLive to get 10% off on the Unacademy Plus subscription. And if you think my content is going to be useful to you, do follow me on Unacademy as well. The link is below. Yeah, it's mentioned in the description. So, good morning, Deepankar. So this channel is amazing. Can you please make a playlist on DSA and C++? So for anything, like first I'd like to I like you all to be good at math first. So anything I do is going to be after you learn math. All right. So good morning Deepankar. And so there's this subscription where you do it's about career as a developer subscription. It's an interesting. It has a variety of interesting shows covering a lot of topics. Who should buy the subscription? Enthusiasts in the software and technology domain who want to enable lifelong learning. It's just $9.99 per year. So check it out. So there is this course which goes live every Friday night at 10 p.m. It starts 6th August. It's by Raj Vikramaditya Striver. You must be very familiar with him. He's an SD at Media and a 6-star CodeChef. I think it's going to be cool. So do check it out. So and there's this other course, CodeChef Apprentice. It's taken by me. It's a show every Saturday afternoon at 2 p.m. It's a course where you So it's a course where like a beginner competitive programmer is like picked, and they come on the show, and I ask about their experience. I ask more questions about their CP and where they're stuck, and why they and what is blocking them to grow further in CP in competitive programming. What's hindering their rating, or what are the main blockers, and I try to answer those questions in the live class. So I think it's going to be, if you're just a beginner with competitive programming, or if you're stuck, if you've been trying it for a while and if you're stuck at your level, And I think that's going to be the right place for you, because I'll be answering a lot of questions, and a lot of questions that person is going to have. And if that person has those questions, chances are you will have it too. So if you think it's going to be useful to you, do attend it. And it goes, it's on every Saturday afternoon at 2 p.m. And I'll also probably be solving a problem in front of him, like a simple problem, like just to run through his thought process, giving him hints and so on, as a fun endpoint. So there's that. So again, yeah, it's going to be taken by me, and I think it's going to be educational for you as well if you want to grow at it. So check it out. It starts on 14th August, which is I think tomorrow. So what are the Plus subscription benefits? So you get to interact with India's best programmers, and there are going to be live interactive classes. There's going to be complete doubt support, and you can practice problems in CodeChef. And if you have any doubts with those problems, you can get them clarified with India's best programmers as well. So here's a subscription model you can see on the screen. So, and use the code SciLife, don't forget it, to get 10% off on the Unacademy Plus subscription. So if you think it's going to be useful to you, this channel is going to be useful to you, do click the subscribe button, because if you're a beginner, I think it is going to be useful to you, and do like and share it with your friends if you think it's going to be useful to them too. So first problem, just looking at the chat. Hello Bayo, how many years takes 7-star in CF? I'm not 7-star in CF, I'm 7-star in CC, CodeChef, and it took like 3 years at least. Actually, I'm working in swiggy.com. I start CP, or it's too late. It's not too late. It's definitely not too late. Don't worry about that. All right. Awesome. All right. So let's start off with the question 9. So Chinese reminder theorem basics. It's a huge word, a Chinese reminder theorem. And what are all these variables? P1, P2, R1, R2, or P1 and P2 are primes. Don't worry. Let's simplify. So given P1, P2, R1, R2, we're given 4 numbers, P1, P2 and R1, R2. Find a number which gives a reminder R1 with P1. Find another number which gives a reminder R2 with P2. P1 and P2 are different primes. Find a number X which gives reminder R1 with P1 and R2 with P2. So say the question was just, and here down are the constraints, P1 is under 1 billion and P2 is also under 1 billion. So Rohit asks if I'm good. Yeah, I'm great. How are you? So if the question was just find X where X modulo X gives a reminder R1 with P1, then the answer would just be R1, right? The number R1 gives the reminder R1 with P1. Straightforward. Now you are given two such things. X should give a reminder R1 with P1 and R2 with P2. Got it? Like for example, I'll show it to you. Where is my scratch pad? Okay. I forgot where my scratch pad is. Awesome. All right. So the question. You're given P1, R1, P2, R2. You need to find an X which gives a reminder R1 mod P1 and which also gives a reminder R2 mod P2. Let's take an example first. So let's say P1 is 2, P2 is 5 and R1 equals 1, R2 equals 4. So basically we need to find X which gives a reminder 1 mod 2, it also gives a reminder 4 mod 5. Can someone tell me an X which is an odd number which gives a reminder, odd number which gives a reminder 4 modulo 5? Can someone just write it on the live chat? Which gives a reminder 1 modulo 2 and 4 modulo 5. What's such a number? There might be some multiple numbers like which are 1 modulo 2, that's all odd numbers, and all the numbers which are modulo 4 modulo 5. What are such numbers? Can you tell me? I'm looking at the live chat. Can anyone tell me? And also you need to subscribe if you want to comment on the live chat. So please do subscribe. All right. So one such number is 9. Like, what are the numbers of the form 4 modulo 5? There's 4, there's 9, there's 1, 14, 19, 24, 29, so on. That's 0 plus 4, 5 plus 4, 10 plus 4, so on. And this number has to be an odd number. So 9 is such a number. 19 is also such a number. 29 is also such a number. So you can print any number which is satisfying these conditions. Any number. So printing 9 is, we can also, if the question is, let's just, no, Rahul, we need to print exactly that one number. There's only one number which satisfies this and this. So 1 does not satisfy 4 modulo 5, right? 1 satisfies 1 modulo 2, but it needs to satisfy both. So 9 satisfies both 1 modulo 2 and 4 modulo 5. It needs to satisfy both of them. Let's take another example. For example, say P1 equals 2, P2 equals 7. I'll just take P1 equals say 3 for example now. R1 equals 1, R2 equals 4. So the number that we take x, it should be of the form 4 modulo 7 and 1 modulo 3 at the same time. So, what are such numbers? So, say we have, what are the numbers that give 4 modulo 7? You have 4 which gives a 4 modulo 7, 11, and add another 7, 18, 25, and so on. So, as we can see, 4 is a number. 4 is the number which gives both 4 modulo 7 and it's also 1 modulo 3. 4 is 3 plus 1 and 4 is also 0 plus 4. Got it? This gives a reminder 4 modulo 7 and 1 modulo 3 at the same time. Now, we are not given these numbers directly, we are given them as variables. As in, given any P1 and any P2, we just need to tell, also we are given R1 and also R2. Yes, 32 is another number. 4 is one number, 32 is another, 32 is not a number because 32 gives 2 modulo 3, right? It does not give 1 modulo 3. So 25 is another number. It gives 1 modulo 3 and 4 modulo 7. Alright. So we given P1, P2 as an input, R1, R2. We need to find an x which gives reminder R1 with respect to P when divided by P1 and which gives a reminder R2 when divided by P2. Alright. So what is the brute force way first of all? Brute force way. Let's check the brute force way first. We can note that, like say x is the solution to this, one sec. Let's say x is a solution to R1 mod P1 and R2 mod P2. Then can we say that x plus LCM of P1, sorry, one sec. X plus P1 into P2 is also a solution. Why? Because if x satisfies R1 modulo P1, then x plus P1 into P2 also satisfies R1 modulo P1 because we are adding a multiple of P1 here. So that won't change the remainder with R1 and it won't change the remainder with P1, it won't change the remainder with P2 either because we are just adding a multiple of P2 here. We are adding a multiple of both P1 and P2 at the same time, P1 into P2. So it won't change the remainder with R1 and it won't change the remainder with R2. Got it? Did everyone get this? If you got this, please say I got it in the live chat so I know you got it. Alright. So if x is a solution, then x plus p1 into p2 is also a solution. Because this won't change the reminders with respect to r1 and r2 at the same time. Got it? Rajkumar, is there a problem here? Like, what's the doubt? All right. Is there any doubt in the question? First of all, like, is the question clear? I want to clarify that first. Is the question clear? If it isn't clear, please let me know. I'll explain it again. Okay, the question is clear, right? All right. So, okay, I'll come back to that. So what I was saying is, one observation is that if there's an x which satisfies r1 mod p1, and then it's all at the same time it also satisfies r2 mod p2. Okay, so Jay, this is the question is that you're given p1 r1 p2 r2. We need to find an x, a number x, which gives a reminder r1 with p1, and at the same time it also gives the reminder r2 with p2. Got it? That's the question. Now if x is a solution to this, like say x is an integer which satisfies this, can we also say that x plus p1 into p2 also satisfies this? Yes, we can. We can say that. Why? Because if x gives the reminder r1 with p1 and r2 with p2, x plus p1 into p2 will also give the reminder r1 with p1. Why? Because it's just adding a multiple of p1 and it won't change the reminder, right? If x gives the reminder r1 with p1, then x plus p1 into something also gives the reminder r1 with p1. If x gives the reminder r2 with p2, then x plus p1 into p2 also gives the reminder r2 with p2, because we're adding a multiple of p2 here. Is it clear now, Rajkumar? Is it clear? I'll tell you why I'm doing this first, like in a minute. Is it clear now? All right, awesome. Let me know if it isn't clear. Now, why am I doing this? This is to tell that if x plus, it goes the same with x minus p1 into p2 also. So if x satisfies r1 modulo p1, r2 modulo p2, then x minus p1 into p2 also satisfies r1 minus p1 into p2. So we can always say that there exists an x between 0 and p1 into p2, which satisfies r1 modulo p1 and r2 modulo p2. Why? Because if there is an x which is greater than p1 into p2, which is greater than or equal to p1 into p2, we just subtract p1 into p2 from x till it lies between this and this. Alright? We can show this with an example as well. So my claim is that you're always going to find an x which is less than 0, greater than or equal to 0 and less than p1 into p2, which satisfies r1 modulo p1, r2 modulo p2. Why? Let's first take with an example, 3 and 7. So say we are given 1 mod and 4 mod 7 as we discussed. Alright. So it should not satisfy. I said there exists an x which satisfies this rule. I'm writing this so that we can just iterate from 0 to P1, P2 and give the answer directly. Alright. Now, 1 mod 3 and 4 mod 7. So we see that 4 is an answer. But we also see that 25 is an answer. 4 plus 21. We also see that plus 21. Like 25 modulo 3 is 1, which is 24 plus 1. 25 modulo 7 is 4, 21 plus 4. And again, plus 21, 46. This is 42 plus 4, at the same time 45 plus 1. 4 modulo 7 and 1 modulo 3. We add P1 into P2 and we can see that 4 is a solution as well. So basically, what I'm trying to do is, I'll tell you why it should satisfy that rule. So, I'm saying there are multiple x's which satisfy Neptune, that's a good one. So, if x satisfies R1 modulo P1 and R2 modulo P2, now we can say that there are multiple possible x's, as we saw. 4 was an answer, 25 was an answer, and so on. But what I'm saying is there will always exist one x which is between 0 less than x less than P1 and P2. Why? Because say we find an x which is greater than P1 and P2. For example, let's say 46. We found 46 that time, right? 4, 25, 46. We can subtract 21 from this repeatedly until it's below P1 into P2. For example, you can subtract 21 from this and you get 25. You get 21 from, subtract 21 from this and we get 4. Which is between 0 and 21. And 7, 3 into 7. Got it? So, if x is greater than P1 and P2, we just we subtract P1 into P2 from x repeatedly till we achieve an x which is less than P1 and P2. Is that clear, Rajkumar? Rajkumar, is that clear? Like, so if it's greater than P1 and P2, we subtract P1 into P2, and we know that if we subtract P1 and P2, subtracting P1 and P2 won't change this property. This property will still remain. The remainders of P1 and P2 will still remain because we are just subtracting a multiple of P1 and we are subtracting a multiple of P2 at the same time. Is that understood? Awesome. Alright. So now what we can do is, we can just iterate from 0 to P1 and P2. P1 into P2. And check which number satisfies R1 modulo P1 and R2 modulo P2. Is there any doubt so far? Any doubts so far? If there are any doubts, please let me know. I'll clear it now. All right. Awesome. So I'll just get to writing the code. It's very short. This is our last class. So I'll just erase this. So we'll just take in the input LL P1, P2, R1, R2, Cn, P1, P2, R1, R2. Just take the input straightforward. Coding spot. Yes, if P1 into P2 is a large number, I know. I'll get to that. First, I'm trying to do the brute force solution so that first we know what it is, what it's about. Like if P1 and P2 are large, this solution won't hold. So I'll come to an optimal solution. Don't worry. For int I equals 0, I less than P1 into P2, I plus plus. if I modulo P1 equals R1 and I modulo P2 equals R2, C out I and L. That's it. Straightforward question, straightforward. Like we decided that there exists a solution between 0 and P1 and P2, and we iterated through all of them. All right. What is the complexity of this? Can anyone tell me what the complexity of this is? Correct. It's O of P1 into P2. But we discussed that P1 and P2, both of them can be up to 10 power 9. And if it's 10 power 9, this is going to take 10 power 18, which is super slow, which is wrong. All right. Awesome. Is that clear? What is another solution for this? So I know that it gives a reminder, X gives us a reminder, R1 with respect to P1, R2 with respect to P2. Now, can I do something smart? So we know that the possible candidates are R1, R1 plus P1, R1 plus 2 into P1. X is going to be one of these numbers. We don't know which one. It's going to be the number which satisfies R2 modulo P2 as well. But it's going to be of this form. R1 or R1 plus P1 or R1 plus 2 into P1 or so on. But we know that if the first number is going to be less than P1 into P2 as well. So what do? We iterate R1 plus P1. So it's going to be of the form R1 plus X into P1. But this number should also satisfy R2 modulo P2. It already satisfies R1 modulo P1 because it's of this form. So we iterate on X. So what we do is, for int X equals 0, X less than R1 plus, I'll just write I'll tell you what it means, less than P1 into P2, X plus plus, if R1 plus P1 into X modulo P2 equals R2, C out R1 plus P1 into X. This is going to take, alright. Now, how is this different? What am I doing here first of all? First of all, here we know that the number has to be of the form. We know that the number has to be of the form R1 plus P1 into X. Correct? Correct. Okay. We know that this number should also give the reminder P2 equals R2. Alright. That's what we're doing here. But now instead of iterating through all numbers from 1 to P1 into P2, we're just iterating over the multiples, the numbers of the form R1 plus P1 into X. Got it? That's what we're doing here. X. But how many times is this loop going to run? Let's check. R1 plus P1 into X less than P1 into P2. So P1 into X less than P1 into P2 minus R1. So X is less than P2 minus R1 by X, R1 by P1. So X is going to run around P2 times, O of P2. Is this clear? And for each X, we are checking if R1 plus P1 into X gives a reminder R2 with P2. Then you're printing that number simply. So it satisfies both R1 modulo P1 and R2 modulo P2 at the same time. And we don't need to iterate infinitely. We just need to iterate for all those numbers which are under P1 into P2. O of P2. So exactly, this is O of P2. So this might be confusing, I understand. I might have gone a bit quick. But let me know if there's any doubt here. If there's any doubt, if any part of it is concerning you. I'll explain it to you again. No concerns. Any doubts so far? Can you please let me know? Any doubts? Please let me know. Or if it's clear, can you please let me know if it's clear as well? Like, if you've understood it, please drop it in the live chat. Alright, I'll explain it again. Can you tell me which part I need to stress on? Alright, no problem. So, what I did essentially was, let's do it with an example first. So what did we discuss? First rule is that whatever that x is going to be there, x is going to be between, we find that x between 0 and p1 into p2. Alright, let's take it with an example. p1 equals 3, p2 equals 7, r1 equals 2, and r2 equals 6. Alright, now we know that the number is going to be between 0 and 21. 0 less than or equal to x less than 21. Correct, because the 21 is p1 into p2, 3 into 7. Alright. We also know that the number will give you the remainder 3x plus 2. The number is going to be of the form 3 k plus 2. Correct. So instead of going through all numbers from 1 to 0 to p1 and 0 to p1 p2, I'll just iterate through numbers which are of this form. That is, I'll iterate through 2, then I iterate through 5. I check if 2 gives the remainder 6 modulo 7. You have the form 6 modulo 7 and 2 modulo 3 at the same time. Correct. 2 gives the remainder 2 modulo 3, sorry. 2 gives the remainder 6 modulo 7. It doesn't. So I move on to 5. I check if it's under 6 modulo 7. Follow 6 modulo, it does not. Then I go to 8. It does not give 6 modulo 7. I go to 11. It does not, because it gives 4 modulo 7. Then I go to 14. 14 is 0 modulo 7. Then I go to 17. It is 3 modulo 7. Then I go to 20. It is 6 modulo 7. And 20 is my answer. That's it. I don't have to go above 21. I already found the answer below 21 itself. So I don't have to go above it. So 20 is my answer. So this is, so I'll do it for all numbers of the form 3k plus 2 which are under 21. So basically I'll do all the numbers of the form. This is 3k. This is basically, this is going to be 3k plus 2 which are under 21. Correct. That's what I'm doing here. R1 plus P1 into X which are less than 21, which are less than P1 into P2. And for each of those numbers, I'm checking if it gives the remainder R2 modulo P2. That is, for example, I'm checking if 2 modulo 7 is giving the remainder 6. 5 modulo 7 is giving the remainder 6. No, it's not giving. And I keep going and I reach 20 modulo 7 gives the remainder 6. And then I print that number and then I'm done. I can just exit here. And I'm doing this till P1 into P2. Is this understood? And I'm going, and this loop is going to run at most P2 times. That's it. Why? Because let's just see how many times loop is going to run. Like mathematical inequality, R1 plus P1 into X less than P1 into P2. This number is greater than 0. Alright. P1 into X less than P1 into P2. So X is less than P2. It's going to run P2 times at most. Right. Is this clear? Please let me know if it's not clear. Like if I solve this properly, I get P1, sorry. X is less than P1 P2 minus R1 by P1. So X is definitely going to be less than P2. Is this clear? Any doubts so far? Please let me know if you're facing any doubts. Rajkumar, it's clear, all right. Rahul, do you want me to explain it again, or is this clear now? So we decrease the complexity from O of P1 into P2 to O of P2. We can make it O of P1 also. We can exchange them, right? It's the same thing. Randy Orton. How is sub buddy? Okay, so Rahul, if you're facing any concerns with no worries. I understand it can be confusing, but I can explain it again. Also, everyone else, like, is this clear so far? If it's clear, please do drop a comment saying it's clear. All right. So essentially, instead of iterating from all numbers from 1 to P1, P1 to P2, I wanted to be a bit lazy and efficient. So I just iterated through the numbers of the form R1 into P1, R1 plus P1 into X, because I know the number has to be of this form, because it gives a reminder R1 P1. All right. Awesome. I'll move on to the next topic then. Actually, the same question. Can I do it faster? So the prerequisites for this is, like, you should have attended in my last video, but even if you haven't, I'll try to make it understandable for you. You need to know Fermat's theorem basically. All right. So the number is of the form R1 plus X into P1. The number is also of the form R2 plus X into P2. R2 plus Y into some other Y into P2. Correct? All right. Or in other terms, let's solve this equation. R1 plus X into P1 should give the reminder R2 modulo P, P2. Correct? That's what it should solve, right? Like, for example, in the previous question, 2 plus 3x should be of the form where I just write the number 7. Correct? Basically, I mean, or you can interchange this. 2 plus 6 modulo 7 equals 3. Or 2 plus 3x is equal to 6 mod 7. Alright. Now solving this equation, we get 3x equals 4 modulo 7. Now x is equal to 4 by 3 mod 7. Wow. But there's 3 in the denominator. Like, it does not make sense, right? Like, it's dealing with integers, now 3 is in the denominator. But wait. Fermat's theorem. We're going to use Fermat's theorem here. And 1 by 3 is, as we discussed, 3 to the power 7 minus 2. Like, 1 by x is x to the power p minus 2 modulo p. Correct? That's Fermat. Like, x power p minus 1 is 1 mod p according to Fermat's theorem. So x power p minus 1 is 1 mod p. X power p minus 2 is 1 minus x mod p. Straightforward. So what are we doing here? So instead of, we can write it as 4 into 3 minus 4 into 3 power minus 1 mod p. And you know 3 power minus 1 is simply 3 power p minus 2, which in this case is 3 power 5. 4 into 3 power 5. And let's check what 4 into 3 power 5 is. It's basically 4 into 3 to the power 5. It's 4 into 243. It's basically 972. And we also added 2. Like, so 2 plus 972. 2 plus 972. 3k plus 2. Yeah. Yeah, alright. 2 plus 972 is 974. One sec. I just made a mistake here. One sec. So basically, what did we try to solve here? One sec. Give me a minute. I just blundered here. One sec. But no worries. We'll get it again. So 2 plus 3x is equal to, sorry, Oh, this is 6, right? 6 mod 7. I took it as 4 actually. 6 mod 7. Now 2 plus 3x. 3x is equal to 4 mod 7. So x is equal to 4 into 3 to the power minus 1 mod 7. And what is 3 to the power minus 1? It's basically 4 into 3 power 5 mod 7. So x is equal to 4 into 3 power 5, we saw it as 972 mod 7. And 972 is basically 966. 966 is the multiple of 7. So x is equal to 6 mod 7. So we can write x equals 6. So instead of here we can put 2 plus 3 into 6. And what do we get here? We very interestingly got 20. We got it very quickly. Alright? Like by just solving that equation. Just sitting there and solving that equation instead of doing brute force, we got the solution. Alright? Let's try it out with a general prime number. Now we know that x has to be of the form r1 plus k into p1. Now r1 plus k into p1 has to be of the form, should we give the remainder r2 with p2, like r2 mod p2. We know that this one already gives us, this is our answer, but we know r1, we know p1, we need to find what k is. So we'll find k through this equation. Okay. Now k into p1 is equal to r2 minus r1 mod p2. Now k is equal to r2 minus r1 into p1 to the power minus 1. We are taking k this side. So we need to multiply by p1 power minus 1. Or we can write this as this also, p1. And then we can write it as r2 minus r1 into p1 to the power minus 1 mod p2. And now after we find this k here, we know how to find r2 minus r1, we know how to find p1 power minus 1 using Fermat's theorem. P1 power minus 1 mod p2 is just p1 to the power p2 minus 2, right? And after this point, we multiply these two and we get k, and this k we substitute it over here, and then we get our x. Is this clear? Do you want me to explain this one more time? I understand this can be confusing. This might be a lot at once. I might have explained it quickly as well. Do you want me to explain it again? I'll explain it for you. Drop it in the live chat, or if it's clear to you, drop that it's clear. Can you drop it's clear, like if you want me to explain it again, I'd like to explain it again too. Unless you won't tell me, I won't know. So did you get it? All right. So I'll just explain it again. I'll explain it in a more cleaner way. So we know that the number x that we are trying to find, it is of the form, it should give the remainder r1 with p1. It should also be of the form r2 mod p2. Okay. If a number is of the form r1 modulo p, r1 mod p1, if a number gives the remainder r1 with p1, it has to be of the form r1 plus p1 into k. Now, our answer is going to be of the form R1 in plus P1 into K. We know R1, we know P1, but we don't know K. Now, we're going to find K by using another piece of information that X is also of the form R2 modulo P2. Now, what did we get here? R1 plus P1 into K, P1 into K is congruent to, or like I'll just write equal to for now, R2 mod P2. Got it? It should satisfy this condition. And from this, we'll solve this equation to get K. Now, how are we going to solve this equation? I'll show it to you. So, P1 into K is equal to R2 minus R1 mod P. We just got this R this side. So, we have to write minus P, minus R1 mod P. Now, we have P1 into K is equal to R2 minus R1 mod P. Now, how do you find K from this? Like we discussed it in a previous video. This is basically P1 into K is equal to some Y mod P. Now, from this, how do we calculate K? So, say we had the equation A into X, A into K is equal to B mod P. Then K is equal to B by A mod P. Now, we discussed how to calculate fractions in terms of modulo, right? We discussed how to do that. How would we do that? It's basically B into A to the power P minus 2 modulo P. We do the same thing here. P1, so K equals, from this we get K equals B into P1 power P2 minus 2 modulo P. P2. This is just P2, by the way. I just forgot P2, but yeah. Did you get this? Is this clear so far? Any doubts? So, all right, I'll get to coding this. Right in front of you. We take the input P1 into R1. Yeah. And now after we get this K, we substitute this K here, and we get the answer. All right. So let's see what K is first. First, let's write the inverse functions that we wrote before. A power B. This calculates A power B. LL inverse. LLA. First, we need to write what the mod is. Let's write the power as well. LL prime. LL prime. Return power A comma prime minus 2 modulo prime. All right. Awesome. Now, what's power? If B equals 0, return 1. Else, LL x equals, like x equals power of A comma B by 2 modulo prime. Now, if B is even, return x into x modulo prime. Else, answer equals x into x. Since B is odd, we just multiplied by return answer into A modulo prime. This is straightforward. We know all this. Now, we know that the answer is of the form K1 R1 plus K into P1. Now, we need to find what K is, and we discuss what K is here. I'll write it again. So, we know that it has to be of the form R1 plus K into P1, and R1 plus K into P1 gives the remainder R2 modulo P2, R2 P2, P2. Now, K into P1 equals R2 minus R1 mod P2. Now K equals R2 minus R1 into P1 minus 1 mod P2, and from this we get R2 minus R1 into P1 power minus 1. Like this is another number to P2. Like we don't care about what P1, if P1 is prime or not. It's just another number. P1 power minus 1 is P1 power minus 1 mod P2 is P1 power P2 minus 2. We discussed that for maths theorem. Correct? Alright. This is K. So let's compute K. R2 minus R1 is basically LLK equals R2 minus R1. First, like into inverse of P2, P1, P2. We know that inverse, like we're just calculating inverse directly. Whole thing modulo P2. Alright. But K can be negative because of R2 minus R1. So we'll just write K plus equals mod. Then K modulo equals P2. If K less than P2, K plus equals P2. Like K is a multiple of P2, right? Because if K is incremented by P2, K is incremented by P2, it's not going to change anything. That's why the actual modulo. Got it? Alright. Now our answer is simply C out R1 plus K into P1. That's our answer. That's simply our answer once we computed K. Or we don't need to write this as well, but it's not. Yeah, alright, got it. This is the answer. Any doubts so far? Any doubts so far? If you have any doubts, please let me know. I'll explain it to you. Any doubts, Yash and or anyone who's in the live chat, like if you have any doubts, please let me know. Please drop it in the live chat. And if you haven't subscribed to it already, please do subscribe. So, hello Venkatesh. So, any doubts? If it's clear, then I'll just give you the like what do you say, the reading for this. I'll give you a link where you can learn from. I'm putting it in the live chat. So this is called Chinese reminder theorem. Yeah. Okay. Yep. Hi Rahul, you're back. So awesome. Now we discuss about the next topic, which is I'll give you another question, which is called the baby step giant step. The baby step giant step question. Yeah. So given A comma B comma P, I won't cover the whole thing in this topic. Maybe like if we have time, we'll cover it. Given A, B, P, find an X where A power X is B mod P. Here the question is different. Find an X where A to the power X is going to be B mod P. Like you're just given number A, B and P, and you want to find, and the prime, this is a different question by the way. You need to find a prime number, like you need to find a number X where A power X gives the remainder B modulo P. You're just given A, B and P. For example, given P, A, B. You need to find a to the power, you need to find x which satisfies a to the power x gives the remainder B mod P. Now, if this mod P wasn't there, if this mod P wasn't there, you could just write x is equal to log of B modulo A. Correct. This is what logarithm means, isn't it? If P wasn't there, like if we just start to calculate x for where a power x is equal to b, then you could just write x is equal to log b base a. That's how logarithms are defined. Now, but there's mod p, so we can't do this. We need to calculate a to the power x. We need to find x is equal to, correct. How do we do this? One thing we know, like how do we do this? One thing we know. Let's write out the numbers a power 0, a power 1, a power 2, so on. A power p minus 1, a power p plus 1, and so on. By Fermat's theorem, again Fermat's theorem is back. So by Fermat's theorem, we know that a power p minus 1, Fermat's theorem, reiterating Fermat's theorem. A power p minus 1 is congruent to 1 mod p. Correct. A power p minus 1 gives the remainder 1 mod p. Now, a power p minus 1 is simply a power 0. A power p is a into a power p minus 1, which means a into 1, which means a into a power 0, which is a. So things are repeating here, right? So, for example, if p is 5, p is 7, for example, we take a power 0, a power 1, so on, a power 4, a power 5, a power 6. We know that a power 6 is again a power 0, because a power p minus 1. I'm taking the reminders modulo p, by the way. A modulo p, a square modulo p. These are reminders modulo p. I'm not writing modulo p because it's gonna get congested in this place. And this so it's easy to understand. A power 6 is also 1 modulo p. Correct. One second. A power 6 is again 1 modulo p. Then we have a power 7. So we can the same as a power 0. A power 0 is the same as a power 6 modulo p. Modulo 7 here. A power 1 is same as a power 7 because a power 7 is just a into a power 6, and a power 6 by Fermat's theorem it's same as 1 modulo p power 7. So on. So what did we notice here? It's powers of a modulo p are repeating after every 6 terms. A power 0, a power 1, a power 2, as we discussed in the last class, a power 5. Then again a power 6 is same as a power 0. It's repeating again. A power 7 is same as a power 1, a power 8 is same as a power 2, so on. A power 11 is same as a power 5. So what did we discuss here in the last class? A power 0 to a power 5 are the only distinct terms, after which things repeat. A power 6 to a power 11 is same as a power 0 to a power 5. A power 12 to a power, 17 is same as a power 0 to a power 5. All of them are same. So, if a power x equals b, this x has to be between like a power 0, a power 1, mod a power 2, so on till a power p minus 2, and then you get a power p minus 1 again. This whole thing repeats itself. So if some a power x is b mod p, then that x will lie between, there is an x which lies between 0 and p minus 2 which satisfies this. Like all powers of a are repetitions of this, right? Are repetitions of this. So if we find which power of a from 0 to p minus 2 gives remainder b mod p, that is sufficient. Is that understood? So what we do is we just compute, we are solving for a power x is equal to b mod p. We just check a power 0, well, lost it. Okay, wait, this is better. That's So we're solving for a power x is equal to b mod p. Now it is just sufficient to calculate a power 0, a power 1 mod p, a power 2 mod p, so on till a power p minus 2. Because after that, we don't need to go further than that. We just need to check if b is any one of these terms. If it's any one of these terms, that's our answer. Like if it's a power 7 or something, which is like a power, if a square is our answer, we are done. We don't need to check after this. Why? Because there is no point checking it. Because if you find some a power x in larger, if x is greater than p minus 2, then you will also find it here. So if you don't find it here, we'll never find it again, because powers of a modulo p are just repeating after p minus 2, right? Is this clear so far? Is this clear? Any doubts? I want you to clear them up here. Awesome, it's clear. Thanks, Rahul. If any of you have any doubts, please let me know. P minus, yeah. So basically, we iterate from a power 0 to a power 1, so on a power p minus 2, and check if a power, any of those a powers is equal to b mod p, and we return that answer. So let's just code it once. We already have the inverse function coded. So take the input. Let's take the input. LL a comma b comma p. T in a b p. For int x equals 0, x less than, we just iterate till p minus 2, because if it's going to happen afterwards, it's going to happen from, if it's going to happen above p minus 2, it's definitely going to happen between 0 and p minus 2. So we don't need to iterate over that. If power of a comma x comma p equals b, C out x, returns it. All right, straightforward. So what is the complexity of this? We are iterating till p minus 2, so approximately O of p, and for each of them we are calculating a to the power x, right? That's again log of, so it's approximately p log p, O of p log p, correct? Is this clear? It's approximately O of p log p, and then we can get x. But we sometimes we might not always get x. Sometimes it's possible that we might not get x. For example, if a equals 1 and b equals 3 and p equals 7, 1 power x is always going to be 1 modulo p, right? It can never be 3. So there are some cases in which it's not possible. So just write return if it comes out PR, no, not possible. Straightforward. Can we shave off? Can we be a bit more efficient here? Yes, we can. So what are we doing here? We're basically calculating a power 1, a power 2, a power 3, a power 4, so on. And each of them is like about log p time, right? Log of p time, because binary exponentiation. How can you make that quick? LL current, I'll tell you how, equals 1. If current, we don't need the current power function at all. Current is equal to current into a modulo p. That's it. So what's happening here? When x equals 0, current equals 1. When x equals 1, current equals a. When x equals 2, current equals a square. When x equals 3, current equals a cube, and so on. So we shaved off that log p factor. So each part is just O of 1. And you're doing this p times. So the whole thing is O of p. So we can get x in O of p time. That's a quicker way, but I'll get to that later. Is this clear? Let me know if you have any doubts. For each power, we are checking if it's equal to b or not. This is simple brute force. We made an observation that the power is going to be between 0 and p minus 2 because after p minus 2, things are just going to repeat. There's no point calculating them. So there's that. Understood? Awesome. Now, how do I get this quicker? How do I make this quicker? Yeah. How can I make this quicker? No. How can I make this quicker? So, I'm solving for a to the power x equals b mod p, right? And I know that x is less than 0 less than x less than p minus 2. I'll just write the 0 less than x less than p, like kuch jata nahi hai, but I'll just write it for now. 0 less than x less than like x is between 0 and p. Now, what I do is, what happened? There was an issue where it took O of p time. But if p is up to 10 power 9, going up till p, it's going to be costly. We can't afford to go up till p, right? That's going to be costly. So we need to do it quickly. So now, what we do is, we do something lazy. Okay, we do something lazy. We write x as all numbers from 0 to p. Why is my phone going off? I'm checking the live chat. Okay. We can write all numbers from 0 to p as r into root p plus q. All numbers from 0 to p can be written as r into root p plus q. Root p, like take the floor of root p. R into root p plus q. Got it? We take all numbers of the form r into root p plus q, where r, like, or talking it in more like general terms, we can basically what you're trying to do here is, we are representing all numbers x from 0 to p as r into let's call root p as b equals root p. Okay, let's take this for now, floor of root p. R into, this is called square root decomposition, plus q. All numbers from 0 to p will fall in this range, where 0 less than or equal to r less than or equal to p by v, and 0 less than or equal to q less than b. All right, wait. This might be overwhelming for you, but I'll explain how, and I'll explain why this is useful as well. So we know that 0 less than x less than p. We know that x is going to be like this. Now let's take p to be 37 for now, just for 37. Now square root of p is about 6, right? B is 6 here. Let's not call that b, let's call that we're running out of variables. So let's call that z. Z equals 7. Z equals, let's call it 6. Floor of square root of p. Alright. Now, we divide 0 to p minus 1 into 30 into 6 blocks of 6 each. So 0 to 5 in the first block, 6 to 11 in the second block, 12 to 17 in the third block, 18 to 24, 18 to 23 in the fourth block, 24 to 30, 24 to 29 in the fifth block, 30 to 35 in the sixth block, and 36 in the last block, but okay. Now this is block 1, this is block, wait, let's call this block 0, block 1, block 2, block 3, block 4, block 5. This is block 6, right? Now, so if R into Z plus Q, if you take any x from 0 to 37, it is going to be of the form R into 7 plus Q, where R is the block number. Wait, sorry, it's going to be R in one sec. I'll just I screwed up. One sec. All numbers from 0 to 37 will be of the form R into 6 plus Q, where R is the block number. Like if the number is say 7, R will be 1, and Q is the index of this number in that block. So, is this clear? Q is the index of that number in this block. For example, if you take the number 14, 14 belongs to the 0, 1, 2 second block, which means R will be equal to 2, 2 into 6, and the index will be 0, 1, 2 plus 2. Got it? For example, let's take a better example. So, say P equals 37, and we want to calculate, and here Z equals 6. Now, we want to calculate X equals, say, for 31. How do we write it as 6R plus Q? Here R equals 31 by 6. The block number is basically 31 by 6. Right. 31 by 6 is 5. 5R. Block number is basically floor of 31 by 6. That is the block number, right? We discussed the first 6 numbers going to the first block, next 6 numbers going to the next block, so on. So the block number for 31 would be floor of 31 by 6, which is 5. 5R plus Q. Here Q is just 1. Sorry, it's 5 into 6. So 31 is basically 5 into 6 plus 1. 6 plus 1. 27 is 5 into 5 plus 2. Sorry, 5 into, sorry, oh man. 4 into 6 plus 3. Here R is 4 and Q is 3. Got this? Is this clear so far? Rahul, could you just say if it's clear? Like if anyone's, I'll tell you why we are doing this. Awesome. Now, what are we going to do with this? So, we know that a power x equals b mod p. Just know that this is a hard topic, and if you don't get it at the first go, that's still okay. And you can rewatch the video to understand. So, a power x is equal to b mod p. Now, we write x as a power r into z plus q is equal to b mod p. Okay. Now where z equals floor of square root of p. I'll tell you why we are doing all of this and then you'll understand. I'll tell you why we're doing all of this. This is going to reduce the complexity significantly. All right. Awesome. Now basically, we know that R can be only, since Z is root P, Q is from between 0 and root P, and R is between 0 and P by Z. I can write this as Z. Oh man, I fucked this up. You can write this as Z. 0 less than equal to Q less than Z, 0 less than equal to R less than floor of P by Z. Alright. Is this clear? Like, so for, if you do this like 0 less than Q less than Z and 0 less than equal to R less than P by Z, if you put all possible values, you'll get all values from all values of X from 0 to P minus 1 or whatever, it doesn't matter. Alright. If we change R, we change the block. If we change Q, we change the number, we change the position in that block. So we cover all blocks and all positions in that block. Did you get that? Does it make sense? I'll tell you where I'm going with this. So it is just sufficient to find R and Q. Now you might think we just arrived at the same problem again, but no. We'll solve this again. We'll solve this in a different way. So what did we get? I'll just write the equation again. Math is just like solving the equation now. A to the power RZ plus Q equals B mod P. Now we just rearrange this. A power RZ is equal to B into I'll just rewrite this again. A power RZ into A power Q. We know Z, we just need to find R and Q. If we find R and Q, we get X. We just need to find R and Q. Our goal is to find R and Q. I know, like you might be thinking, like aren't we doing a harder problem by now? We need to find two numbers instead of just one number. No, I'll just tell you how. This is equal to B mod P. Alright. Now we bring this here. A power RZ is equal to B by A power Q. Now A power RZ, note that we need to find just R and Q. Z, we know what Z is, it's floor of root P. We know what P is, we just need to find, we know what A, we know what B is. We just need to find R and Q which satisfy this equation. There might be several R and Q which satisfy this equation, we just need to find one of them. This is equal to B into A power Q inverse. As I said, Fermat's theorem is a super useful theorem and it's useful here too. So we just need to find A power Z whole power R is equal to, same as like we're just using basic math here, B into A power minus Q mod P. Got it? Or we can just write it as, we can write this as, let A power Z equals D and A power minus 1 equals E. So we're just writing simply. We just need to find D power R equals B into B into E power Q mod P. Alright, that's what we need to solve, isn't it? We know what D is, we know what E is, we know what B is. We just need to find R and Q here. And I'll code it to you how. I'll just tell you how to do it very easily. I'll code it and then I'll show it to you, okay? You need to be familiar with unordered maps here. Like, you don't need to be very familiar, like you just need to know what it does. LL comma LL. R value. Okay. Now for, let's take first what Z is. LLZ equals, so square root of P. Now we fill in. So essentially we have the arrays. So is this clear so far, everyone? Is this clear? Can you tell me if it's clear so far? Okay, I'll just rewrite it. So basically we need to find a power z whole power r equals b into a power minus 1 whole power q mod p. So what we do here is, and r is from 1 to, r is from 0 to p by z, q is from 0 to z. So basically we have two arrays. First array is a power 0, next first, then a power z, a power 2z, a power 3z, basically this, so on. The next array is b into a inverse, b into a power minus 2, b into a power minus 2, and so on. This is the next array. We do this, all of them, we do all of this modulo p, modulo prime. Now if we find any of these two elements equal, we're given to, basically we're given two arrays, we need to find any of those two elements are equal. Alright, this is the giant step, this is the baby step. We're incrementing q by 1. Here this is the giant step. One by one we are incrementing it. Now we have two arrays, we just need to check if any of these two elements are equal. So let's say in the first array a power I z is equal to b into a power minus j. It means that a power I, if two elements in this array are equal, it means that a power I z plus j equals b. Now we know what I and j are, we know what those equal elements are, so we can retrieve I z plus j directly, and our x would be a power x equals b. The solution for this would be, x equals I z plus j, and that's our answer. We're going to do that now. Now first let's make both the arrays first. Like, you don't need to make, but and how do we do that? Actually we can do it without making the arrays as well. Why need to make extra space? There's no need to waste extra space. So for int I equals 0, I less than, let's call this r, r less than 0, r less than equal to p by z, r plus plus, r value of, once I write the code you'll understand it, power of a comma r into z equals r. Now for int q equals 0, q less than z, q plus plus, what is LHS? LHS is basically this part, b into a power minus 1 power q, high coefficient, b into power of, you know what, I'll just LL equals power of a, inverse of a, basically inverse of a power minus 1 power of inverse of a comma q. And now LHS equals b into e modulo p. So basically LHS will have this part. And here, okay, now if we find this LHS anywhere inside this map, that is if R value dot find LHS is not equal to R value dot n, then x equals minus 1, or x, the answer, x equals R value of LHS into Z plus Q. Break. Now if x equals minus 1, C out not found, else C out x. This is, I think, the Cobalt team, the Sublime, not sure. I'm not sure, man. I need to check, but let's not digress. Ankur, one sec. Let me discuss this first. So, all right, what did we do here? First, this is basically power of a power z power r. We are filling it in the unordered map. Now, here, this is basically b into a to the power minus 1 whole power cube. Now, if we find this value will be this. If we find this value anywhere inside the unordered map, that is, if we find this anywhere inside the unordered map, it means that we found a matching, like we are going this one by one. We're going from here to here, then here to here, one by one. We find this anywhere here. This is our unordered map. We find this anywhere here, then we know its R value. We are marking this with the value R. So we know what the R is. And you know what the Q is here. We are iterating through Q. So from R and Q, we can find what X is. Right. From R and Q, we can find what X is. X is just IZ plus J. Got this? Now at this point that we know what R and Q is, and from R and Q we can find X very quickly. And from this we get the solution of a to the power x equals b. We're given a, we're given b, we're given p. We can find x using this logic. Now we are iterating through R and we are iterating through Q, but we are iterating through them separately. We are not iterating through them in the nested loop. We are iterating through them separately. And we are seeing if any of them matches. If even one of it matches, we know our answer. We know which block it's present in, and we know what the offset. Once we know which block and which offset, we can compute x directly. Got it? Our block number is determined by R and our offset is determined by Q. Once we know that, we can get x directly. And the complexity of this is just p by z. And p by z is approximately root p. So this is going to be root p. And this is going to be root p as well. Root p times, it's going to be iterating. It's going to iterate root p times, but power is log of p. Root p log p. So we reduce the complexity from O of p to O of root p log p. Is this clear? Can you tell me if it's clear, or if you want me to re-clarify something here, I can re-clarify it too. Is this clear? This is root, one sec. This is root p. Like it's iterating through root p, but each power is log p. This is also root p, but each power is log p. So the total complexity would be root p into log p. Is this clear? Yep, Rahul says it's clear. Kage Musha says it's clear too. Awesome. So let's go with another optimization here. Like as if like this is sufficient, but we don't need to, like, we can optimize it a bit further. We can chuck off the log p, and I'll show you how. So this is basically, what is this? This is a power, it starts with a power 0, then it goes with a power z, then it goes with a power 2z, and so on, a power 3z, and so on. So instead of computing power each time, we just compute it once in the start. LLD equals a power of a comma z, and after this point, LL current equals 1, and then current equals current into D each and every time. We just write current here. Look, so quickly we just eliminated a log p from this loop. We had to eliminate it from this loop, but we eliminated from this loop very quickly. What did we do here? Current equals 1 at the first time. First time current equals 1. Next time current equals a power z. Next time, like when r equals 2, current equals 2z, a power 2z, because we're multiplying current with a power z. Then it becomes 3z. So at any given r, current will be equal to a power rz. Is this clear? This should be clear. Like this is a similar optimization what we did previously to optimize. At every point, current is being multiplied by d. Got it? All right. Let me know if it's clear. Now, again, we do the very similar optimization here. LL equals, let's say f equals inverse of a. Now, again we write current equals 1. At the end of the loop, current equals current into f. Now we can chuck this, and we can just write current. Well, we can just write this. Actually, you know what? Yeah, current. All right. Now what's happening here? What's happening here? So what we did here is, initially current equals 1. The next step, after this is when q equals 1, q equals 0. If q equals 1, current will be multiplied by f. So current equals a power minus 1. If q equals 2, current equals a power minus 1 multiplied by a power minus 1 again. This is basically a power minus 1. Current equals a power minus 2, and so on, a power minus 3. So for a given q, current will be equal to a power minus q. So we eliminated a log factor here as well. Unordered map finding is amortized O1, so we don't need to worry about that. So at each point we found current, and from that we found what LHS is, and we find if LHS is present in any of the R values, and we are done. We found our x here in O of root p. Note that we eliminated log p from here. We eliminated the bottleneck. We eliminated what the power function is doing, and we just did it lazily. We just did it once for all, and then we computed it incrementally by multiplying it by what it needs to be multiplied by. Is this clear so far? Can you drop in the chat if it's clear, or if there's any doubt? If you want me to repeat something, I can repeat it too. Is this clear so far? Rahul, can you tell if it's clear? Both Rahuls and Kagimusha, and people who are watching, if you understood this, can you please drop in the live chat if it's clear? Know that you need to subscribe to actually comment on the live chat. This is pretty cool, right? So awesome. So this is using cryptography and things. Cryptography, like just to simply calculate x, and I don't know the actual application, but it is used, and it's called baby step, giant step. So this is the giant step where we are skipping the blocks, and this is the baby step where we are trying to find what the offset is. I want you to understand this. This is an application of Fermat's theorem as well. So first we did O of P. Like first we did O of P log P, and then we improved it to O of P. After that we even further further improved it to O of root P log P, and then we eliminated the log P by doing by computing the power exactly once, like only once, and then incrementally multiplying it to what it needs to be multiplied by. Did you get this? Yeah. This is clear so far. Any doubts? Awesome. All right, folks. So I'll be taking a class. Also, I'm going to take a coach of apprentice next on tomorrow. So if you think it's going to be useful to you, like as I said, if you're a beginner, it's probably going to be useful to you because I'll be giving tips and advice on how to improve in computer programming. So I'll be there's going to be a coach of apprentice, and I'll ask where they're blocked in their improvement and how to improve further. I'll be helping them with that. So it's mostly going to be a one-on-one mentorship, but just that you'll be able to see that, because if you're a beginner, you're likely going to relate to that person. So if you think that's going to be useful to you, please do check it out. It's going to happen at 2 p.m. tomorrow. All right. Awesome. Then have a great day. See you tomorrow.